This lesson is on the fundamental theorem of algebra. So before we get into that, we're going to look at the connection between zeros, factors, roots, and intercepts. So if you look at our example, so everything I'm going to say in my example is over in this leftmost box, but I think it makes more sense if we look at a real example. So this particular polynomial, this quartic, is graphed over here on the right. So if you'll notice that this graph crosses the x-axis here, 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 and here 4 times. And notice that the highest degree is also 4. So we have 4 zeros here, and notice those zeros occur at -3, -2, 1, and 2, and they corresponded to our x-intercepts, -3, 0, -2, 0, 1, 0, and 2, 0. Now, the related function, or the equation, is simply not going to have the, like this has the p of x. That makes it a function. It has 2 variables. When we're looking at just the equation, it's just going to have an equation equal to 0. So it's not going to be equal to that y, or that f of x, or p of x in this case. But notice that our solutions are the exact same. We end up with -3, -2, 1, and 2, which would correspond to our factors. So what that means is if I was to factor this polynomial, these factors would give me these roots, which correspond to the zeros. So these things are all interconnected, and it becomes very important as we start solving more complex polynomials. So when I talked about there being 4 solutions to this polynomial, that comes from what's called the fundamental theorem of algebra. So what the fundamental theorem of algebra tells us is that if there's a polynomial of degree n, so any degree other than 0, so first degree, second degree, third degree, fourth degree, all the way up to whatever degree you want, then that equation is going to have at least one solution in the set of complex numbers. Now, it's easy to think that when we say complex numbers, we're meaning imaginary numbers. But if you'll recall, both real numbers and imaginary numbers belong to the set of complex numbers. So both of those different number sets, the real numbers and the imaginary sets, they live within the complex set. So a real number is a complex number. It's just purely real as well. An imaginary number is a complex number. It's just a pure imaginary. And then you can have a mix of a real with an imaginary part. Okay, so real is part of complex. So this theorem says that there's at least one solution in the set of complex numbers. Now, there's a corollary to that. What that means is it's kind of like it's like an add-on. So it says that if f of x is a polynomial of degree n, again, where n is not 0, it's got to be more than 0, then the equation has exactly n solutions. Okay, so that means if it's a 4th degree, it has exactly 4 solutions. If it's a 7th degree, exactly 7 solutions. Now, this is provided that each solution repeated twice is counted 2 times, or if it's repeated 3 times, it's counted 3 times. So you're counting those repeated solutions. Okay, so all polynomials will have that number of solutions. Now, there is something you need to kind of realize about these solutions. If a solution is complex, a complex solution will always come in pairs. So what that means is if your solution was 2i, you would also need -2i. Complex solutions always come in pairs. Okay, so if we're looking at case 1, so there's 2 cases that we're going to look at when we're finding zeros of polynomial functions. The first case is one we've worked with before, is where the polynomial is factorable. So for example, we're going to find all the zeros of f of x equals x cubed minus 3x squared minus 2x plus 6. So the first thing we're looking at is the fact that this is a cube. So this is a cubic, which means we can have up to 3 solutions. Now if we think about this logically, this means we could have 3 solutions that are completely real, all real numbers, just purely real. We could have 1 solution that is purely real, and then 2 solutions that are complex, because complex solutions always come in pairs. But we couldn't have 3 complex solutions. So we have to have at least 1 real solution. So 1 real and 2 complex, or 3 fully real solutions. So to start this, we're going to let this function equal 0. So x cubed minus 3x squared minus 2x plus 6 is going to equal 0. And we're going to try solving it by factoring. So this is 4 terms. So in order to factor this, we would group the first 2 terms. So x cubed minus 3x squared. And then make sure there's a plus in between. and then we would group the second two terms. So that negative 2x plus 6. Okay, so now our GCF of our first set of terms is going to be x squared, and then our leftovers would be x minus 3. So x squared comes out of the first group, x minus 3 is left. The second group, we'd have a negative 2 that comes out, and we would be left with x minus 3 as well. So now, this is our common factor, this x minus 3. So we would write down x minus 3, and then times, what's left is x squared minus 2. Okay, so, for example, those are the factors of this polynomial. So what that means is this right here could be rewritten as f of x equals x minus 3 times x minus 2. And you're noticing I'm not finishing factoring x squared minus 2, because it doesn't factor. So x minus 3 is linear, it's done. X squared minus 2 is quadratic, but it's not a difference of squares. So since 2 isn't a perfect square, I can factor no more. So now I need to figure out the solutions. So I would set each of these pieces equal to 0. So x minus 3 equals 0, and x squared minus 2 equals 0. The first equation, we would simply add 3. So x equals 3 is the first solution, and we expected at least one real number, and that is a real solution. Now our second part, we're going to set equal to 2, so add 2 to both sides, take the square root of both sides, so that's the absolute value of x equals the square root of 2, which means x equals plus or minus the square root of 2. Now, the square root of 2 is a real number. It's irrational, but it's still real. It's not imaginary. So this means that we have 3 full real solutions. They're fully real, purely real. So we would say our solutions are x equals 3, x equals positive square root of 2, and x equals negative square root of 2. So you could list all of them, or you could write that with the plus and minus. And again, either way is appropriate for the solutions. Now I do want to show you that you can check this with the calculator, because we know that the graph is going to have x-intercepts, and those x-intercepts should correspond to our solutions, at least the real solutions. And since we have 3 real solutions, we should see 3 crosses on the x-axis. So if you look here, I've graphed this. Notice that this particular function has an intersection, has an intersection point here, here, and here. It has 3 real zeros. Now the problem with using the calculator is we sometimes get tempted to rely on the calculator. And while yes, we can see that 3, 0 is one of the real zeros there, the square root of 2 is not going to show up on the calculator. Okay, so you still have to depend on your algebra skills in order to solve those quadratics, because I want the exact answers. I don't want decimal approximations. If you use the calculator, you're going to get a decimal approximation. And even here you can see that one of our zeros falls between -1 and -2, and the square root of 2 is between -1 and -2. And then you can see the other one falls right here between +1 and +2. Again, we know that that's going to fall between those two numbers because the square root of 2 is 1 point something. Okay, so I want exact answers. Oops, sorry. This is an exact answer. I want those square roots. So you might want to make a note. The calculator is a really good way to check to make sure your zeros make sense. It would be a good way to check if your zeros are rational, but if they're irrational, you've got to do the work. Okay? Now what happens if the polynomial is not factorable? I'm so glad you asked. So, we're going to find all the zeros of this new polynomial. Well, if I set x cubed minus 2x minus 4 equal to 0, it doesn't have 4 terms, so I can't group it. I could try to solve this by using our quadratic form, but there's a little problem. This is x to the first. In order to use this, my highest degree here would have to be x squared, because remember it has to be double the middle term. So double 1 is 2. So x cubed, so this is not going to factor in any of the ways that we know how. So what that means is we've got to come up with another way of possibly solving this. So this is where understanding your polynomials comes in handy. This is a degree 3, which means it has to have at least one real solution. So if we look at the graph of this particular function, so if I pull up our graph, so this is x cubed minus 2x minus 4. If you notice in this picture, it has one solution right there that crosses the x-axis. So based on this particular picture, I already know that I have one real solution and the other solutions are going to be imaginary because this graph only intersects the x-axis one time. But I have to find all the zeros, so I need to know what those imaginary numbers are. So what we're going to do is we're going to figure out that factor. So it looks like x equals 2. So it looks like x, what in the world is going on? I'm sorry guys. X equals 2 is what that graph looked like. Now we can maybe check the table and notice the table does say 2 0, so that's helpful. If I wasn't sure, remember we could also use the remainder theorem. So just a reminder, the remainder theorem simply says that if you plug in this value into the function, so if we evaluated at f of 2, we should get 0. So 2 cubed minus 2 times 2 minus 4, well that's 8 minus 4 minus 4, which equals 0. So this is for sure a solution to this. This is going to work. Okay, so that means our factor is going to be x minus 2. That's the factor. X equals 2, so x minus 2 is the factor. Well, how does that help us? Well, knowing the factor is going to allow us to figure out the other factor. And remember, to do this, we would have to use long division. So that's what we're going to do next. We're going to take and we're going to divide x minus 2 into x cubed. And then remember, we need a 0 term for 0x squared minus 2x minus 4. This is where polynomial long division comes in handy. Okay, I know it can be tedious sometimes, but without this skill, we're not going to be able to figure out that other factor because this is not factorable by hand. Okay, so we're going to do the long division. So x into x cubed is x squared. So x cubed, and then x squared times negative 2 is negative 2x squared. So remember, we have to change the signs because we're subtracting. And that's going to leave me with positive 2x squared. And then we're going to bring down the next term. Do it again. X times 2x squared is positive 2x. Multiply it back. So 2x squared minus 4x. We're going to subtract. So minus and a plus. That becomes positive 2x. And we bring down our last term, negative 4. X goes into 2x 2 times. So 2x, 2 times negative 2 is negative 4. Again, we're going to subtract. And here's the thing, guys. We should get a 0 as a remainder, which we knew we were going to get because we saw the remainder theorem. F of 2 equals 0. X minus 2 went into this function. We have 0 left. So what that means is this x minus 2 is a factor. And we have this other new factor now. This x squared minus 2x, or sorry, plus 2x plus 2 is our other factor. So now that we know that we have these two factors, now we can set them equal to 0 and solve. So now I can finally solve this equation. So x minus 2 times x squared plus 2x plus 2 equals 0. And now I know this is not going to, this x squared plus 2x plus 2 doesn't factor more, and the reason I know is because my other two solutions have to be imaginary, which means we're going to have a negative discriminant, which means it's not going to factor. So we can set x minus 2 equal to 0. We already know that's going to be a solution of 2. We already figured that out graphically. And then this x squared plus 2x plus 2, I'm not even going to try to factor it because I know it's not going to. So instead, I would want to use one of my solving for quadratic methods. So we could complete the square. This one would work okay with that. Or you could use quadratic formula. Personally, I think quadratic formula works just as well. It's whichever your preference is. So I think most people default to quadratic formula, so that's what we're going to do. So I'm going to put x equals, remember it's negative b, so negative 2, plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is 2, all over 2 times a. So now negative 2 plus or minus the square root. Alright, so we have 4 minus 8. 4 minus 8 is negative 4. So right there I can see there's my imaginary solution, because I hit the square root of negative 4 would be 2i. And our very last step would be to simplify. So remember, when we're simplifying this, we're going to do negative 2 divided by 2, which is negative 1, and 2i divided by 2, which is just I. So our solutions for this particular problem are going to be x equals 2, and x equals a negative 1 plus I, and a negative 1 minus I. So notice we do have 3 solutions, and you could write this the way we have it here, 2. So this x equals 2 and negative 1 plus or minus I, you could write it, just list those numbers as well. Still 3 solutions. Okay, we expected 3 solutions, we got 3 solutions. And checking graphically, we could see that only 1, 0 was on the axis. Okay, so this is what we do when it's not factorable. It's a little more work, but it can still be done. Alright, so looking at number 1, it says find all the zeros of this function. So I want you to go ahead and pause the video and try this. I will give you fair warning, it's not factorable. We've worked with factorable ones, so you're going to have to come up with another way. So start by looking at the graph and see if you can come up with the solution to number 1. Alright, hopefully you're ready to see the answer. If not, go ahead and pause the video again. So the first thing you would have wanted to do is look at the graph and notice that this function actually does have 3 real zeros, because notice it's going to cross here, here, and here. Unfortunately, the only one that I know for sure is that x equals negative 3, because that's the only one that crosses at a nice value, an integer. So that's called an integral 0. So x equals negative 3, you could check it using the remainder theorem, or you could just divide it and notice that the remainder is 0. And then you're going to take that remaining quadratic and you're going to solve. So again, you could use quadratic formula. This one again works really well with complete the square because the bx is even. So when you use the quadratic formula, you should have got that the discriminant was 12, which it should be positive because we have 3 real solutions here. So no imaginary parts. 12, if you will recall, has a perfect square. So this 12 can be rewritten as 4 times 3. So the square root of 4 is 2, the square root of 3 stays. And then where you have to be careful is that 4 can be divided by 2, so 2 times. 2 divided by 2 one time, and 2 divided by 2 one time. So being very careful when you're doing that division. So this was from the last chapter, so it just keeps coming back. So if you got this one correct, if you got negative 3 and the solutions 2 plus or minus the square root of 3, give yourself a little check in the corner. Okay, so I know that you got it right. And then let's move on to the next one. Alright, last one, number 2. It says find all the roots. Now notice the directions are a little different here than in the first one we did. So in number 1 it said find all the zeros. Well, that's because we were looking at a function. Now we're looking at an equation, just a polynomial equation. So the first thing we should notice is that the degree is 4, which means we would expect this to have 4 solutions. So 4 real solutions, 2 real solutions, and 2 complex, or 4 total complex. Now our hope is that it's going to have at least 2 real solutions, because otherwise we're going to have a hard time with this. So the first thing we would want to do is we would want to get this polynomial equal to 0. So to do that, we're going to have to subtract the 20. Our next step is to look at our graph. So when we look at this particular function, here's what it looks like. So it doesn't quite look like a polynomial the way we're used to it looking, but it's just because it's a little big. So we know this graph is going to open up with our 2 arrows going up because it's an even degree and the leading coefficient is positive, which means our minimum value is somewhere down here, further down in the y. So if we wanted to see it, we could. We don't need to see it. All we need to be able to identify is our zeros. So if you look here, we can easily see that this graph crosses twice, which means we have two real zeros. And if we look at the graph, it looks like -4 and 1. If we look at the table, it also looks like -4 and 1. And again, we could double check by using the remainder theorem and seeing if when we plug those in, if we get 0. So we're thinking x equals -4 and x equals +1. So we have two factors. The problem is getting that last factor. So we already have two. We need one more. We need a quadratic to solve. Because since we have two real zeros, that means the other zeros have to be complex. And remember, they're going to be complex conjugates because they're going to be, they come in pairs. So what we need to do is we're going to take these values and we're going to have to do some division. So remember, x equals -4 is simply the factor x plus 4. And x equals 1 was the factor x minus 1. So by knowing these factors, we're going to be able to get some information. So I'm going to start with x plus 4. It really shouldn't matter which one you start with, so if one's giving you some trouble, try using the other one. But since I looked at x plus 4 first, that's the one I'm going to use. So what I want you to do is once you get this set up, I want you to do the long division and see if we get the same answer for what's left. So go ahead and pause the video. Alright, so here's what we should have gotten. X cubed minus 5x squared plus 9x minus 5. Now, if we were to multiply x plus 4 times x cubed minus 5x squared plus 9x minus 5 back, we would get the original answer. But we're not trying to go back, we're trying to go factors. Again, we cannot factor this x cubed, this cubic that's left. So what that means is, we have finished with this first factor, x plus 4. Now we have to factor our new expression with x minus 1. So that is what we're going to do next. We are going to take x minus 1, and we are going to factor x cubed minus 5x squared plus 9x minus 5. So I don't want to go back to the original. I want to go from the new polynomial because I'm trying to get smaller factors. Okay, because I'm trying to get down to at least a quadratic. If I can get to a quadratic, I can solve a quadratic. So again, go ahead and pause the video, use the long division to get this down to a quadratic. Alright, so hopefully you got x squared minus 4x plus 5. And again, we know it's a factor because we saw it on the graph, and we have a zero remainder, which is what our remainder theorem tells us. So now I finally have a quadratic. So what I'm going to do is I'm going to take my three factors. Yes, 3. So our three factors are x plus 4, x minus 1, and this new quadratic. So we're going to take and we're going to write those down. So x plus 4 times x minus 1 times x squared minus 4x plus 5. And this all equals 0. So if we were to multiply all this back, we would again get that original polynomial if you wanted to double check. Now, I don't need to sit here and solve x plus 4 and x minus 1. I already know the answers. My answers are -4 and +1. The only thing I need to worry about is solving that quadratic. So that's what we're going to do. We're going to take x squared minus 4x plus 5 and set it equal to 0. Now again, we can solve by quadratic formula or complete the square. Since we haven't done one with complete the square in a while, I'm going to do this one with complete the square, but you can always use quadratic formula. So just a reminder, when we're completing the square, the first thing we do is move the constant over and make sure that the x squared has a coefficient of 1, and this one does. So then we're going to take and we're going to add something to both sides here. And that something is going to be half of 4, which is -2, squared. So we're going to add 4. Basically, we're adding 4 to both sides, guys. So then we're going to factor x minus 2 squared equals -1. Well, then we're going to take the square root of both sides. So the absolute value of x minus 2, the square root of -1, if you recall, is I. So there's our imaginary. We knew there were going to be two imaginary solutions. So then x minus 2 equals plus or minus I. So x equals 2 plus or minus I. So our solutions then, our final solutions, would be x equals -4, +1, and 2 plus or minus I. And notice 2 plus or minus I, those are called complex conjugates because they're the same values but with a different sign in the middle. So same numbers, different sign. And imaginary numbers always come in pairs, those super complex solutions. And then we have our 2 real roots, which we could see on the graph. Okay, so that is the end of these notes. Go ahead and put this in the notes section of your notebook, and you're done with this video.